This is the first online virtual class in this lockdown situation. We'll be starting with where we left off in the class. In the chapter of linear transformations, we had started with the definition of a linear map and examples. Today, our main goal is to see a proof of what is called the Rank-Nullity theorem. So, let's start. First, we recapitulate what is the definition of a linear transformation. So, the definition goes this way. If V and W are two vector spaces over the same field F, a function T from V to W is called a linear map if for all alpha beta in V and C a scalar from F for all vectors alpha beta from V and scalar C from F, we have this thing, that T of alpha plus C beta is equals to T alpha plus C times T beta. Fine. So this is the definition of linear transformation. So and we have seen as immediate consequences. So let me write consequences. Number one is T of theta V is equals to theta W. Okay, where theta V and theta W are the null vectors in the vector spaces V and W respectively. And secondly, we have for all vector alpha in V, we have T of minus alpha is equals to minus of T alpha. So you must realize that this T of minus alpha, this is a vector in this minus alpha is taken in the V minus of alpha, and here minus of T alpha is the inverse additive inverse of alpha minus negative of T alpha in W. So these two are the immediate consequences. This also we have seen in the class. So next we define what is called rank and nullity. So the subset of T, so this is also a definition, let me mark it. Definition: the subset of V which gets mapped to theta in W is called the kernel of T, and is denoted by let me see, is there no kernel? I'll write this way. Oh yeah, fine. Kernel of T. Okay, so that is mathematically writing. Ker T is the set T inverse of theta W. Okay, all the pre-images which gets mapped to theta W. So this is all the vectors in V such that T of alpha is equals to theta in of course, in W. Fine. So this is the definition of kernel of T. As we have already seen that theta v, the null vector in V, this is in car T, obviously. This is in car T because theta v gets mapped to the null vector in W. So therefore, car T is something non-empty subset of V. So therefore, car T is not empty set. Yes, car T is something non-empty. So this is an easy exercise that, so show that this is a very easy exercise that car T is actually is a subspace of V. I would urge you to prove this one. This is an extremely easy exercise. Now, when we have this, I'll write this exercise, exercise 1, let's say, so that car T is a subspace of V. Now, when we have the fact that car T is a subspace of V, the dimension of car T we can something talk about. So this dimension of car T, this gives us the next definition that dimension of the subspace kernel of T is called the nullity of T, and is denoted by N of T. Now, so we have got the definition of what is called the nullity. So next we need to define what is the rank of the linear transformation T. So now let's look at the range or image of T. So let's look at range of T. We denote it denoted by image of T. This empty means image of T. Now what is this? By definition, there's nothing to do with linear transformation. This is the definition of an image of any function. So image of T is all those elements, so T of alpha, where alpha is coming from V. So all the T images of vectors from V. Fine. Now this is another easy exercise. To show that empty is a vector subspace of W. Of course, empty is a subspace of a non-empty subset of W, and actually it is a subspace of W. So again, when we have the fact that empty is a subspace of W, we can talk about the dimension of empty, and this is called definition dimension of the subspace empty of W is called the rank of T, and is denoted by simple R of T, rank of T. Fine. Now, so after these two definitions, we are at a position to state our main theorem, the Rank-Nullity theorem. So I'll just copy it from here. Rank-Nullity theorem. Okay. So this says, I'll stop the underline and bold. Okay. If V is a finite dimensional vector space, and over a field F, and W is another vector space over the same field F, then and T is a linear map. T is a linear map from V to W. Then we have this as our consequence, that rank of T plus nullity of T is equals to the dimension of V. Okay, now you must understand that why we need V to be finite dimensional. So if it says if V is a finite dimensional vector space over a field F and W is another vector space over the same field F, then and T from V to W is linear, then rank of T is equals to rank of T plus and nullity of T is equals to dimension of V. Fine. Okay. So now, before looking at the proof of this one, we need two lemmas in our hand. So lemma 1, this says that a linear map T is T from V to W is 1 1, that is injective, if and only if curl T is only the set, this one, the trivial kernel, what we call. So kernel of T has got only the null vector from V inside it. So if T is 1 1, then curl T will be trivial and vice versa. So a proof of this goes like this. Assume T is 1 1. Assume T is 1 1. Then the proof is simple. Then the proof is trivial actually. You see, if T is 1 1, then we have seen that here T of theta V is equals to theta W. So therefore theta V is there in kernel of T, obviously, and since it is 1 1, there is no other element which maps to theta W. Hence kernel of that one, kernel of the map T will be theta V only. Conversely, assume that curl T is equals to this trivial set theta V. Then we need to show that T must be 1 1. Then we show that T must be 1 1. So let for two vectors alpha and beta in V, T of alpha is equals to T of beta. So then what happens? Therefore T of, I will write this in the next line. Therefore T of alpha minus T of beta, T of beta is equals to theta W. This implies T of alpha minus beta is equals to theta W. Again, this implies that alpha minus beta is in kernel of T. But what is kernel of T? Kernel of T we have fixed it to be only theta V. There is no other choice. So therefore alpha minus beta is equals to theta V, and this implies alpha is equals to beta. Okay, hence T is 1 1. So we are done with the first lemma. The second lemma goes this way, that if T from V to W is 1 1, then and this set alpha 1 till dots alpha n is a basis of V, then this set T of alpha 1 till T of alpha n, this set is a basis of W. So this is our second lemma. Let's see the proof of this one as well. Choose a vector beta, which is a vector beta from the image of T. So since beta is image of T, then beta must be some the T image of some vector alpha in V. So for some vector alpha in V. Now, as I'll call this as S, I'll call this set as, say, S or B. This was the notation I was following in the class. So as B is a basis of V and alpha is in V, we must have scalars Ck is equal to 1 to n, such that alpha will be sum of these things, sum of k running from 1 to n, obviously Ck alpha k Ck alpha k. Therefore beta, which is T of alpha, is T of this thing, this sum of this thing. I'll copy and paste here this one. So I can also put something k runs from 1 to yeah, to the power n. If I write, no, nothing happens. Okay, let it be. So k runs from 1 to n. I'll do something over here only then. 1 less or equal to k less or equal to n. Okay, so this one is by definition. So this is by definition of the linear map. This is sum k equal to 1 to n. Yeah, this works now. So this is ck into t of alpha k. Okay, so you see, therefore beta is, so beta is in the linear span of these t alpha k's. Beta is linear span of these t alpha k's. I'll call this beta 1. Okay, I'll call this one beta 1. So here this one I call this as beta, not beta, why am I saying beta? Beta b1. So beta is in the linear span of b1, the over there t alpha 1 to t alpha n. So therefore, hence now beta is any vector from image of t. So therefore, image of t will be a subset of L of b1. Okay, we need to show image of t is equal to linear span of b1. The other implication, the other inclusion L of b1 subset of image t is trivial. Because these things t alpha 1, t alpha 2 up to t alpha n, these are all vectors in image of t, because they are all t images of alpha 1, alpha 2 up to alpha n. So since these are all t images, these are all vectors in image of t, and image of t is a subspace, so their linear combination, any linear combination will also be in image of t. Hence linear span of b1 is also a subset of image of t. Therefore the L of b1, linear span of b1, is equals to image of t. So the spanning set, so therefore this t alpha 1 to t alpha n is a spanning set of image of t. Next, we actually need to prove this is the basis of, sorry, I'm very sorry over here. This is not W, this must be int. Okay. So since we need to show that this is the basis of image of t, we need to show the linear independence as well. So assume for scalars ck, k is equal to 1 to n, k is equal to 1 to n, this thing happens, that sum k is equal to 1 to n, ck t alpha k is equals to theta in w. Then what happens? Therefore this thing is equal to sum of I'll copy this one once again, paste, yeah, no, sorry, Okay, so this is Ck alpha k. Okay, and this is entirely of t. Yeah, so this one is equals to theta w. Theta w is equals to this. So this implies that this quantity over here, belongs to, is in kernel of t, because t image of this quantity gives you theta w. So therefore this quantity must be an element in car t. But what is car t? We have t is 1 1, hence by lemma 1 car t has to be theta v. So therefore this belongs to car t, and car t is nothing but theta v. There is no other choice. Hence, so therefore this one is equals to theta v. Why am I writing this one? Making the same mistake. Okay, so therefore this equals to theta v, and this implies that all the ck's are 0. Ck's are 0 for all k, because this one, ck alpha k, this one is a linear combination of the vectors from this B alpha 1 to alpha n, and this is a basis of V, and this basis vectors, a linear combination of these basis vectors is equal to the null vector. Hence this has to be the trivial linear combination. All the scalars must be 0, so ck's are all 0. Now what are ck's? Ck's were the combination scalars for which the scalar linear combination was giving the linear combination, it was giving that ck tk alpha k summation ck tk alpha k is equals to theta of w. Hence, since ck's are all necessarily 0, the elements tk alpha k, that is tk alpha 1, tk alpha 2 up to tk alpha n, these elements must be linearly independent. So therefore, hence B1 is linearly independent, and hence is a basis of empty. Okay, so now we finally at a position to prove the rank-nullity theorem. So let's start. So proof of rank-nullity theorem. Okay, so let's address the extreme cases first. The extreme cases are case 1 is nullity is 0. Nullity is 0. That is curl T is equals to the null vector theta. Curl T is the null vector theta. Hence, by lemma 1, T is 1 1, and hence by lemma 2, if I'll copy this one once again, if this is a basis of V, Then this one, this T of alpha 1 till T of alpha n, then this one is a basis of empty. Hence we have got, hence rank T plus nullity of T. So you see, rank T over here is the dimension of the image space, and the image space T alpha 1 to T alpha n is a basis of image space. So rank is the dimension of this the number of elements in this basis, that is n, plus nullity is 0, so that is n, and this is our dimension of V. All right, because dimension of V, because alpha 1 to alpha n is a basis of V, so obviously the dimension of V is alpha 1 to alpha n. So this is done. Case 2 is nt is equals to the n, which is dimension of V, is equals to n. So in that case, what happens? So the entire space V is the is in the kernel, is the kernel of T. So therefore, kernel of T is equals to V, the entire space V, isn't it? Nullity is the kernel is a subspace of V, and if its dimension is equal to V, then the kernel has to be the entire space V. So kernel of T is equals to V. What does this imply? Then what is my image T then? What is my image T? Nothing but the null vector. There is no other way. This is the zero map. T is the zero map. Hence, again in this case as well, as you can see, rank T plus nullity of T is equals to, so rank is 0 here because image T is the trivial subspace, zero space, and plus nt is n, so 0 plus n is equals to n. So these two are the extreme cases. Now let's come to some proper cases. Okay, so here here I'll need B1. Okay, let's say B1 as alpha 1. All right, before that, let me write, let nt is something, I'll denote it by capital N, and so yeah, this is the notation I'm going to follow in this particular case. So let nt be n, and which is and obviously this is strictly more than 0, n, and strictly less than n. So we have considered the extreme cases in case 1 and case 2. So this is a proper case, a proper non-trivial case. So now in this case, let B1 is equals to alpha 1 till alpha 1 till alpha n be a basis of kernel of T. Be a basis of kernel of T. Therefore, by extension theorem, we can extend B1 what is showing here. Therefore, this one, yeah. Therefore, we can, by extension theorem, we can extend B1 to a basis, we call it B2, as alpha 1 till alpha n, and after this we'll add alpha n plus 1. Sorry, what is happening? Yeah, I forgot this one. Alpha n plus 1 and dot dot alpha n. Yeah. All right. So this is my basis. So we have adjoined. So we can extend the basis B1. We can extend the basis, this basis, to a basis of entire space V. Basis this of V. Fine. By adjoining these elements, alpha n plus 1 till alpha n. These elements we have adjoined to the basis B1 of curve T and have got the basis, this B2 as the basis of V. Very good. So our job will be show. So this is it is enough to show that these elements, the T images of these adjoined elements, show that I'll call this one as B3, which is T of alpha n plus 1, this thing, and up to T of alpha n. These elements is a basis of MT. Now let's spare a moment to observe that why this one proving this fact is enough to prove the theorem. So if this one is a basis of V, then this one is a basis of image of T, then what will be the dimension of image of T? That will be small n minus capital N. That will be the dimension of image of T, hence the rank of T by the definition. And we have assumed that the nullity is capital N, so therefore rank plus nullity will be small n minus capital N, that is the rank, plus nullity, which is capital N, which will give you the dimension of V, that is small n. Okay, so it is enough to show that this one is a basis of image T. Fine. So we need to prove two things: spanning set and the linear independence. So for spanning set, we go by the same thing. So let beta is equals to T alpha is in MT. Beta is as T alpha is in MT for some alpha, some vector alpha in V. Then as B1 is not B1, B2 is a basis of V. We get scalars Ck, k equal to 1 to n, such that I'll write this in the next line, such that some sum k runs from 1 to n, ck alpha k, again, yeah, this is equals to alpha equals to this. So this implies beta, which is t of alpha, is equals to t of this entire thing. So this is I'll write this again, and I'll write t of alpha k here. This goes by the linearity of t. Now at this point you see t of alpha k is running from 1 to n. So what are these things? Alpha 1, alpha 2 up to alpha capital N, then alpha capital N plus 1 up to capital alpha small n. So from the first capital N many vectors, the t images are all 0, because these vectors are vectors in the kernel of t, are basis from the kernel of t. So t of alpha 1 to alpha capital N, these things, they do not contribute anything. So this one is basically this entire same thing, but k is running from capital N plus 1 to small n this time, because from 1 to capital N there is no contribution in the sum. So this is the entire thing. So this means that this beta is in linear span of this thing. So therefore image of t is a subset EQ of linear span of b1 b2 b3. This is, yeah, linear span of b3, right? And again, as like the other earlier case for this one, this lemma 2, in the other inclusion is again trivial. I'll write this one again. The other inclusion is trivial for the same reason stated there. So therefore image of t is equal to linear span of b3. Fine. So there, hence we are done with the spanning part. So next we need to show the linear independence. So then for that, assume for scalars k equal to n plus 1 to n, plus 1 to n, we have this thing, that what do we have here? Yes, I just change this one, n plus 1 equal to theta w. So we need to show all these ck's are 0. So this implies this one, that t of this one is equals to theta w, and then again this implies that this quantity is in kernel of t. But what do we know about kernel of t? In kernel of t, this b1, where is my b1? This one is a basis of kernel of t, and this one is an element in kernel of t. Hence, or let me write, since B1 is a basis of kernel of T. There exist scalars say dk, k is running from 1 to capital N, such that what do we have here? I'll remove this capital. Okay, fine. I'll copy this one, paste it here. Yeah, so I'll paste it once again. This equal to this, so I'll have this one capital N. This is dk alpha k is equals to over here capital N plus 1 to this one, right? Am I doing something wrong? Oh yeah, over here k equal to N plus 1, k equal to N plus 1. Yep. So those are printing mistakes. Okay, so now we have finally got here. This is all fine, no mistakes are here. So this means this implies that one minus the other is the null vector over here. So this one I'll write minus of this thing, minus of this quantity, plus this quantity is equals to theta in V, obviously. So now look at the last line over here. Look at the last equality over here. What is this one? This one is a linear combination of the vectors from B2, see, capital alpha 1 till alpha capital N, alpha capital N plus 1 till alpha small n. All these vectors are present here. So this one is a linear combination. I'll write, but this one is a linear combination of the vectors from B2, and since that is equals to the null vector, since B2 is a basis, and this linear combination equated to null vector must imply that all ck's and dk's are 0. ck is equals to dk are all 0 for all k, right? So we are done. Hence this ck's, we need to show that we needed that ck's must be 0 in this linear combination. This ck's are all 0 in this one. So, and that we have got. Hence this vector, so hence B3, that is these vectors are linearly independent as well, is linearly independent as well. Hence B3 is a basis of MT, and we are done. Therefore rank T plus image T is equals to, so rank becomes the number of elements in B3, that is small n minus capital N, this is my rank, I'll put it in the bracket, minus capital N, and rank plus nullity. What am I doing? Yeah. So rank is small n minus capital N and nullity is capital N, that is equals to N. This is dimension of V. So this proves the theorem. This PDF will also be is also uploaded in the description of this video. Thank you so much for your patience.